Okay, we're getting started. Hello, everybody out there in TV land. I'm hoping today will be kind of an interactive session. So please here on campus ask questions, and I'll ask Audricha over there to track Piazza questions, please. Anyways, today's lecture is about the navigation problem that is coming up due next Monday. So I was just going to go over the statement of the problem and approaches to solving the problem, and like I said, looking for questions from you on the project. There were some people on Piazza who felt like they needed a little more information that wasn't in the recorded lectures, so I'm here to answer that information now. Why don't we start by me sort of reviewing the actual project itself, and then we'll look at code a little bit. Let's get to the right spot here. Okay, so we're talking about MC3 Project 2 Q Learning Maze Navigation. Let me make this a little bigger so everybody can see it. Okay, so the overview is let's turn this microphone on. You should first implement a Q learner. And I provide an API a little bit further down that shows you essentially the functions we should be able to call. It's very similar to when you created the learner that we tested in the last learning project. Only this one is, of course, reinforcement learning instead of the regression learning that you were doing before. When you pull the directory from GitHub, you'll see that there is already a file there called qlearner.py, and the one reason for that to be there is essentially if you implement your code within that file, we'll be sure that you're implementing the API correctly, because it's got all the function prototypes that are correct. Right now, I think it just returns a random action, so it's not going to work too well. But at least it'll integrate with the test learner. Okay, so by the way, coding the Q learner correctly is worth 95% of the grade. So we're going to test it with a number of different navigation problems, but the core important thing here is for you to implement the basic Q learner correctly. There's another 5 points available if you implement Dyna correctly, and we'll test that with 2 test cases. Anyways, one key thing that, for you to remember here is, yes, we are testing your Q learner in the context of a navigation problem, but your Q learner doesn't really need to know anything about the navigation problem. Our code that tests your learner adapts the navigation problem to something that works for a reinforcement learner. And similarly, when you do the last project in the class, the Q Learning Trader, you're going to have to write code similar to test harness that we have in order to make your QLearner work correctly in a trading environment. Okay. So here, yes, update your local directory using GitHub, and you'll see QLearner there. And right out of the box, you should be able to test it by typing Python test QLearner. And what's going to happen, by the way, if you do that, is it's not going to work very well because it's just doing random actions, right? So as soon as you correctly implement QLearner.py, then it'll start doing the right things. Okay, here is the API that we want you to implement, and I go through and I talk about all the parameters. In fact, why don't I just do that right now and see if anybody's got questions about it. So the first important function for you to implement is the constructor, and the parameters are num states. So that's how many states are there in your problem. So in our case, it's exactly 100 because the robot is navigating around a 10 by 10 square, and so the answer there is 100. Again, we provide test code that's going to call you with the right parameters here. I'm just telling you what they mean. Now, what do you do with that number, num states? That's one of the things you want to do in your constructor is to initialize a Q table. And a Q table is simply a 2D array of floats, and one of the dimensions of that is num states, the other dimension is num actions. So in our case, we have 100 possible states and 4 possible actions, so we've got 100 rows by 4 columns. Alpha is the learning rate. So we talked about that when I was going over QLearning the other day. This is essentially how much do you trust new information when you're updating your Q table. This number is always between 0 and 1, and 0.2 is kind of a typical value. Gamma is what is the value of future rewards. So in other words, let's say gamma is 0.9. What that's saying is a reward one step into the future is only worth 90% of what it would be if I got it right now. So the immediate reward is always full value, but future rewards are discounted by this gamma value. Now, one thing that's kind of weird about this problem is until you reach the goal, all rewards are negative. Each time the robot takes a step and doesn't reach the goal, it gets a reward of -1. Let's forget about the quicksand thing for a moment and think about what does that tend to motivate the robot to do. A way to think about it is that essentially because it's getting a negative reward until it reaches the goal. I think I mentioned this last time. It's like you just got out of the pool and your feet are wet and you're walking across an electrified floor, right? You want to get the hell out, right? So in the same way, your robot wants to get to the goal so that its feet stop getting shot. Does that make sense? Sounds kind of cruel, right, to the robot. I don't know what to say about that other than it works. Okay. However, when the robot finally moves onto the goal state, it gets a reward of +1. So if you think about this, it's trying. The stated objective for the learner is to find a policy that maximizes reward. It still may end up being a negative number, but the way it can best maximize reward is to get to the goal in the fewest number of steps possible. And again, gamma is saying how much future rewards are discounted by. RAR, or random action rate. One if you look at if you look in the book, or if you look at one of the original Q-learning papers, you'll see that one of the things that makes it work is early on it should choose random actions occasionally. The reason for that is if you don't do that, there's nothing that will necessarily force the learner to explore, to try, when it arrives in a certain state, to try a different action than it tried last time. So using this random action rate is a way to do that. And this is a number, again, between 0 and 1 that indicates the probability that at each step it will choose a random action. Now that random action rate should decay over time and eventually become 0. So once you have a perfect policy, you don't ever want to take a random action because that might cost you something. It will cause your policy not to be optimal. So you start with that being non-zero, but then you decay it over time so that it approaches 0. And how do you decay it? Well, it's using this decay rate, random action decay rate. So this is a number between 0 and 1, and each time your agent takes a step, you multiply, you just have a simple equation, RAR equals RAR times RADR. So that means it'll shrink by a little bit each step, and we specify, if you take a look at, we'll take a look at it in a second, if you look at testqlearner.py, you'll see the numbers that we use for these two parameters when we call you. Dyna, normally this is set to 0, and what that means is how many Dyna updates should you do. So for the plain QLearner that you do first, don't implement Dyna, just ignore that parameter. But when you add Dyna to get that remaining 5 points, then you need to pay attention to it. And we'll talk in a minute about what Dyna is. And then verbose, of course, if that's equal to false, don't print anything. If you do, it'll potentially slow down the autograder, and you don't want to do that. And we'll always call it with false. Okay, so that's the constructor. Once that's called, everything should be set up with your QLearner. Then this is the primary function that implements QLearning, query. And the way it works is we call you, our test harness calls you repeatedly over and over and over and over again and says, okay, this is the new state you're in, S prime, and this is the reward you get for the last action that you took. And query should return an integer, which is the action to take. And the steps that you need to follow within this function are first, update the Q table, because you've got new information here. You realize you're in a new state and you're getting a reward for the last action you took. Now you need to separately remember, so you need to use a local variable to remember what was the state I was in before and which action did I take. So you have to remember S and A, right? And then you're told S prime and R, and those four things are all that you need to update your Q table. So an experience tuple, again, is S, the state you were in, A, the action you took, S prime, the new state, and R, the reward for having taken that action. And again, you use those to update the Q table. Anyways, stepping through what you do in query. Update the Q table. Roll the dice to decide whether you should take a random action or not. So remember, there's that RAR, the random action rate. So roll the dice to see if you take a random action. If you do, then choose that random action and return it. Also, you need to update RAR. And again, that's just RAR equals RAR times ratter. Now, if you're still stepping through this code, you have chosen not to take a random action, and you have updated your Q table. So what's left for you to do now is to determine what action should I take. And remember, your Q table is the answer. Your Q table answers that problem for you. So what you do is you go to your Q table, you go to the row S prime, that's the new state you're in, and you look at the Q value for each of the actions that you might take, and you just choose the one that has the highest value. And that's the action that you take. And that's it. That's all that you need to do in query. It's probably maybe 20 lines or something. It's not a very deep function. There's one other function you need to implement that is kind of sort of a special case, and it's called query set state. And all that, remember when I was telling you up here, when you implement query, you need to remember the last state you were in and the last action you took. Well, if this is the very first action we're asking you to take, you can't remember it. It's like when a baby was born, asking it to remember, hey, what was it like yesterday? It can't know that. So what query set state does is it says, okay, this is the state you're in. Save that. Don't update anything, just except for that state. Just remember that's the state you were in, and then we'll start calling you with query. Okay, that is the whole API that you should implement. I haven't said anything about navigation. I'll get to that in just a second. But before I do, any questions about this API that you should implement?
Based on the RAR value, we are supposed to decide whether or not to take a random action.
Right.
How exactly do we do that?
Oh, okay. So, so the question is, you're supposed to choose a random action with probability RAR. Okay. Here's a way to do it. Simple. Call a random number generator that should generate a random number between 0 and 1. And if what comes back from the random number generator is less than RAR, you take a random action. Okay. Any questions from Piazza? Okay. Is anybody on Piazza acting like they're alive? Like, are they seeing this?
Apparently, you are at 10% and you should plug in.
Oh, that is very helpful. Dave, give that person a bonus. Thank you in TV land. Thank you so much. Okay, any questions here in Georgia Tech land? Okay.
I guess I got it.
Sure.
This may be more navigation, but or applied to the trader. But it's kind of obvious we have 100 states because we have a 10 by 10 world. And it's kind of obvious that you constructed it so we can only go in 4 directions. But even in the navigator, we could go in 8 directions because we could go diagonally.
Right.
And it actually converges faster if we set a date. But how do you know those for some other problem besides this one? Number of states, number of actions.
So the question for those who couldn't hear, Pat said, in this particular problem, we know ahead of time there's only 100 states. We know there's only 4 actions. But what about for the actual trader? How do we know how many states there are? And well, we're going to predefine that there's only 3 possible actions. Anyways, a lot of success in applying a machine learning algorithm to a problem involves what do we call it? Mapping the problem you're trying to solve to the problem that the learner can solve, right? So the short answer is it takes human craftsmanship. I know that's not a very satisfying answer, but you need to consider what the algorithm can do and map your problem to that. So some of the decisions you're going to have to make are, well, I'll give you an important trade-off. How fine or how high resolution do you want to consider your factors? So for instance, we talk about discretizing your factors into an integer so that you can plug into your Q-learner. Well, if you choose for each, let's say you're using 3 factors. If you choose to have 1,000 different increments for each one of these factors, you've now got 1,000 cubed states, right? Now, a problem with that is when you're learning, when you're training your system, you may visit only a fraction of those states. So when you go to actually use what your learner has learned, you're going to be querying states that you've never visited. So making these really high resolution actually causes your learner to overfit and to not know what to do in lots of situations. So that's an example of a trade-off. There's another kind of solution to that, but let me get to that a little bit later. But long story short, you should probably experiment with a couple different resolution settings on those factors. Having very small, low resolution means that your learner can probably generalize a little bit better. If it's a little bit like having a large leaf size in a decision tree. If you have a smaller number of bins with these factors. Anyways, the answer to your question, how do you know which one to do? The answer is, I don't know if there's really a theoretical answer, but the practical answer is start with low resolution, see how well it works, and if it doesn't work well at all, start bumping it up a little bit and see experimentally if it gets better. Okay, probably a longer answer than you wanted. All right, any other questions in the back?
So the update to the truth table is just for state A and state S and action A. Is it just updating the reward value into that particular cell in the truth table? Is that?
Yeah. So it's. I'll show you. I thought. Well, there I am. Cool. Well, let me just go to Udacity. Udacity. So the question is, by the way, what is the Q update? And I'm just going to show that to you. This is the update rule. So on the left is the new value of QSA, and that's calculated in the following way. You take your old value and multiply it by 1 minus alpha. You calculate an improved estimate, and that's alpha the learning rate, times the immediate reward that you just got, plus gamma times the later rewards. And that's the update rule. This later rewards, by the way, that's just another, that's a value from another part of the Q table. Okay, any other questions? Okay. Okay. All right, that's the API. Let me talk now about this navigation problem. Once you check out the code, you'll see that there's a subdirectory there called test worlds. And these are just a bunch of CSV files. And I'll show you one here. So you've got 13 of them. Make this a little bigger. Here's an example of one. So it's just a CSV file with integers and commas, and 0. And so these represent what's in each of the cells in our grid world. So we've got 10 by 10. 0 means it's empty space that you can navigate over with no penalty. 1 means it's there's an obstacle there. 2 is the initial location of the robot. And 3 is the goal. And the objective is for the robot to navigate to the goal, and incurring, you can view it as the lowest cost or the highest reward. And because the rewards are negative until you reach the goal, you're incentivized to get there quickly. Now, there are these special things, I call them quicksand. And if the robot steps in quicksand, it's a reward of -100. You can go through it, but you get this penalty. So one thing, if you look at this particular navigation problem, the shortest way to get to the goal in this case is to come over here, go along this wall, and go directly to the goal. You might think, okay, that's the policy that my learner will converge to. Well, one reason that it shouldn't, and I hadn't mentioned this before, is in real world problems, you might choose to go in a certain direction. You might direct a robot to take a certain action, but sometimes it doesn't act perfectly. There's some noise in the way the robot interacts with the world. And what that boils down to is every now and then the world moves you in a random direction. So if your robot happens to go along this wall, there is some non-zero chance that when it tries to go north, it'll go east and it'll hit that quicksand and get the -100 reward. So when we run the learners, they start initially trying to learn to go along here, but after they hit the quicksand a couple times, they learn that it's better to go over this way. In fact, I'll run it real quick so you can see what it looks like. There you go. Let's make sure I have the right world here. Okay, so this is going to it's going to try to solve the problem 500 times. So we'll see 500 results go by, and we'll let them go by. Let me stop it for a while. So you can see it's already, let me just let it go. We'll see. No, there we go. Okay. Let me run that again, sorry. Okay. So after 500 iterations, it learned this path. It goes to the right around these obstacles and gets a total reward of, well, gets a median reward of -31. One thing to mention here is the score that we're going to give you is we're going to take the median of your reward for each of the 500 results. So a reason for that is it turns out that if we were to give you a score that was just your shortest trip, you might sometimes get lucky by going along the wall here. And we don't want you to learn to just sometimes get lucky. We want you to actually learn learn an optimal policy, which in the end is to avoid the quicksand over here. Now, one thing that's kind of interesting about this, by the way, of how it relates to trading, is essentially going along the left here represents a kind of strategy where you might get lucky and get a good score, but occasionally something will go terribly wrong, right? Whereas if you go along the right side here, you will very reliably get to the goal every time. So it's analogous to risk versus return, and kind of showing that if you can quantify the risk, like in this case, we're telling you the penalty may be 100, negative reward of 100. You can actually calculate whether it's better to act more conservatively or more risky. Okay, so that's looking at that example. I think I covered all of this. Anyways, in terms of transforming this problem to a problem that a Q-learner can solve, here's what you have to do for any problem. If you want to see if a reinforcement learner can solve it, you need to define what are the states. And in our case, for this problem, the state is the location of the robot, and it's simply a number that we calculate as the column times 10 plus the row. And that'll give us numbers between 0 and 99. There's 4 possible actions: move north, east, south, and west. R is the reward. So you have to, for instance, in your trading problem, you have to decide, is my reward going to be the return for each day, or is it going to be delayed until I exit the position, or maybe something else? You could reward yourself, for instance, based on the Sharpe ratio of how well things have gone since you entered the position. Anyways, the last thing is the transition matrix that defines the problem. Now the learner doesn't know R and T, and that's the magic of Q-learning, is that it still is able to solve the problem. Let me show you now a little bit of what the code looks like that's calling your learner, just so you can see that. So this is where it starts, test code. In this case, we turn verbose on because we do want to print a lot of stuff. When we're calling you, it'll be set to false. Anyways, we read the file in, and by the way, you get this code. we read the file in. It's just a bunch of numbers, and so boom, it goes into a empty array. Then we print the map. We set a random number seed. We call your constructor with these parameters, and then we say we've got a separate function called test, and we tell it, okay, we want you to test this learner over 500 iterations, and then it goes at it and returns what the reward was. That's the core of the code. Let me show you what test looks like. Here's test. Okay. So what we do is we do a loop iteration numbers of times. So 500, we do what's below here 500 times. We set the reward, our accumulated reward to 0. We put the robot in the starting position. We figure out its what that corresponds to in our state. We tell the learner, okay, we're in this start state, and then we start going. And each iteration here, we say, hey, learner, this is your new situation. This is the reward for the last thing you did. Tell us the new action. And then we check to see whether we hit the quicksand and so on. And anyways, just iterate. I don't think it's worthwhile going into all the nitty gritty of this. But each time you give us an action, we move the robot. Of course, there's some random chance it may go in a random direction, which is separate from your learner choosing to make a random action. We accumulate the total reward, and boom, that's the resulting score. Okay, that is really it for the initial part of the Q-learning problem. Any questions on that? Yes?
Did you say that even this test code might decide to take a random action apart from the random action decided by your robot?
Right, so there are two ways that random action occurs. One is your learner chooses to reply with a random action. The other is that the world says, screw you, you want to do that? No, we're doing this. And that's a separate, here I'll show you where that is. And what that reflects is just the general, so we're solving a class of problems called Markov decision processes. And they include the possibility that the transitions to other states are not fully deterministic. And so that's what's happening here. So our random rate, the probability with which the world will move you in a different direction is 0.2. And so here's people were asking, how do you decide if we're going to do something random? This is exactly that determination. We essentially roll the dice by calling a random number generator. And if that's less than or equal to that random rate, boom, we're going to do it. Then we choose a. You can use almost exactly this. I did not want that. Am I hearing Emacs jokes? Anyways, you can use exactly these two lines of code. Change the names, of course, but that'll work within your Q-learner for choosing a random action. You don't even need to take the picture because you got the code already. You pull it from GitHub. Okay. Any questions on what I presented so far? Okay, let me talk a little bit now about Dyna. The formal lecture will be about Dyna will be on Thursday. It's also on Udacity, but I'll mention it a little bit since I know I'm not going to separately talk to the folks online before then. So let me cover a few things about it. Here's the idea for Dyna. So the first observation is if you imagine that this code was actually controlling a robot, and when we say go north, the robot, takes a step north. It actually takes a second or two for the robot to move, a real robot to move 1 meter around in the world. So if you created one of these worlds for a real robot to navigate in, you would discover that learning a navigation path in a 10 meter by 10 meter area is extremely expensive in terms of time, right? I mean, even if the robot can move 1 meter per second, it's going to take, even if it could get directly to the goal, directly, it would take at least 10 seconds just for it, even if it knew the perfect solution. But these, if you look, when you run this code, you'll see, in the first time when it takes 500 tests essentially for it to learn a decent policy. So you'd be looking at least 500 times 10 seconds. So what is that? 5,000 seconds. So a long time. Now, what Dyna does is it lets you take advantage of the experience that you've already had in the world and refine your Q table for each real experience you take in the world that is expensive. It lets you converge your Q table many, many more times so that the number of experiences you have to have with the real world are greatly reduced. So in fact, when you run Dyna, or when I run Dyna with my solution, I converge to often a better solution after only 50 iterations than 100. So you converge to as good a solution with only 1/10 of the cost of interacting with the real world. So Dyna is important when your interactions with the world are expensive. Now, one thing that's going to happen is when you, well, let me describe how Dyna works, and I'll talk about it again on Thursday. But here's the way Dyna should work. Remember I said earlier, we don't have T and R. We don't have this transition matrix, and we don't have R, the reward function. What you can do, though, is as your agent interacts with the world, you can build a model of T, and you can build a model of R, and I'll go into the details on Thursday, or you can look at the Udacity lecture. But basically, here's how you build a model of T. Remember, T is it's a table that has 3 dimensions or 3 parameters. S, the state you're in, A, the action you took, and S prime, the state you ended up in. And T is just the probability that you end up in that S prime state, given that you were in state S and you took action A. So all you have to do to build this T is count. Each time you're in state S and you take action A, you observe what new state you end up in, and you just count for each possible subsequent state. You count how many times you ended up in each one, and just define the probability as based on that count. You can build a reward function the same way too. Every time you get a reward in the real world, you know what state you were in, you know what action you took, and you can just build this R, again a lookup table, R of S comma A. Okay, so that's how you build T and R. Now, if you have T and R, here's what you can do, and this is the heart of Dyna, is when your query function gets called, your QLearner query function, you do everything just like normal. You update your Q table, but before you pick your action, we'll move the update RAR and choose your action to after Dyna. Here's what you do for Dyna, is you hallucinate an experience. I don't know a better way to describe it. It sounds a little bit informal, but actually if you read papers about things like Dyna, it's not me that invented it, I don't think. Anyways, you hallucinate an experience. Well, how do you do that? There are a couple different approaches, but essentially, here's one way to do it. Choose a random S, choose a random A, and then look at your T, which is the probability of the subsequent states you'll end up in. Consult it and pick the subsequent state according to that probability. So now we have an S, an A, and an S prime. And we can also go check our reward function. We just look up R of SA, and that's our hallucinated R. So we have totally hallucinated an experience, but it's based on one that we've actually had in the past. We take that hallucinated experience and do a regular Q table update, but we do that a large number of times. And the number of times you do it is whatever the value of Dyna is set to. In our case, I think we call it, let's see, I think we call it with 200. So in the non-Dyna case, it's 0, of course. And then when we're testing, if you implemented Dyna, we call it with 200. So you do this, you hallucinate 200 experiences and update your Q table with each of those experiences. And what happens is your Q table converges to the right solution much more quickly in terms of interactions with the world. Now, the runtime of your program is actually going to be longer. But don't confuse, that doesn't mean that Dyna is a bad idea, okay? Because keep in mind, imagine if your program was running on a real robot, it could do all these Dyna updates easily, as the robot moves through the real world. It can do 200 Dyna updates certainly in much less than a second, that it would take the robot to move. So indeed, yes, your program is going to run slower with Dyna, but that's not the same as the fact that the policy is actually converging more quickly in terms of interaction with the world. Same thing goes for if you were writing a QLearner to do trading. Each one of those trades is expensive, right? So you want to learn milk as much policy information as you can from each time you interact with the world. So that's another reason Dyna is good even for trading. Okay. Now, one thing I want to point out regarding Dyna, and this is one of those things where you get extra value for actually coming to class or reading to or listening to the video all the way to the end, here it is. I'm not going to lay it out explicitly, but I'm going to give a big giant hint. Okay. The intent of Dyna is that you sample from experiences you've already had in order to update your Q table. That does not necessarily require that you build a T or an R. There are other ways to do that. Let me restate. The intent of Dyna is that you sample or hallucinate from experiences you've already had. Constructing a T and an R is one way of doing it, but there are other ways of doing it as well. And in terms of my criteria for determining whether you've implemented Dyna or not, is really primarily the test is that your policy converges to a good value in many fewer iterations. Dyna is one way, the traditional implementation of Dyna is one way to do it. There are other ways you can implement Dyna or something similar to do it as well. So that's the secret bonus. Any questions? Yeah.
Do you sample from experiences with a large reward or very small cost? Or do you weight those? Do you give those a higher probability of being sampled, or do you sample?
Yeah. To repeat the question, should the probability that you pick a historical experience depend on what the reward was? So it might be, in some sense, more valuable to choose the ones with high reward or low reward with higher probability. I think that would, I don't know the answer to that. However, I would say, so it'd be an interesting experiment. I would say though that because the secret to why Q learning actually works, at first it doesn't seem possible that just based on the state you're in, this Q table could tell you what to do, because the value of this action depends on all the actions you do after it, right? So how does it learn to go around the obstacle? When it's just starting from the first movement, how does it decide to go that way around the obstacle when it's going to be multiple steps before it even encounters the quicksand? And the way that happens is that the negative rewards centered on touching the quicksand have to kind of propagate back through the Q table one step at a time, all the way back to the start location. And so, in some sense, updating the Q table in just sort of these ordinary states is important, because it's even in those sort of ordinary empty states that you need to get directed away from the quicksand. So long story short, I think the answer is you discover it's probably not worthwhile to emphasize those expensive ones, but it might provide a little bit of an edge. Any other questions? Anything from TV land?
Dave's taking care of most of it.
Oh,
Sitting here answering them.
oh, okay, cool. Is there anything I should answer for the video?
The primary questions are just a couple of folks thinking that the learner is responsible for things that happen in the environment.
Oh,
How does the learner not know to walk through a wall? How does it know its action moving north, south, east, west? Which
Right.
the answer is it doesn't.
okay. Worth addressing if you implement Q right, you don't even have to. A well-crafted Q learner doesn't need to know anything about the problem it's trying to solve. It's just trying to find a Q table that maximizes reward. So one thing that people often get tripped up on is they think somehow that they need to convert the robot's location into a state. And for this problem, you don't have to. That happens automatically for you. Okay, let me ask one more time if anybody's got a question. Okay, two. Okay, start with Dave.
The other thing I answered on Piazza that you might want to mention is the way that we do an entire pass through a single query function has confused a few people because it's kind of the second half of one time step and the first half of another time step. Mm-hmm. You might just mention that it sort of spans two time steps.
Sure, good question, or good point. So to repeat, let's go back and look at the functions you need to implement. So again, query is the heart of the query function is the heart of your QLearner. And remember, the core is that update rule. And in order to complete an update, you need to have state, action, S prime or the subsequent state, and the reward for having taken that action in the last state. When your function query gets called, it's only given the last two of those. It's told the new state you're in and the reward you got for your last action. So the only way you can fill in that gap, the only way to get all four of those things, is you have to remember, so you save it in a local variable, you have to remember, last time I was in state S, so save that. Essentially you have a line kind of like S equals S prime just before you return. That's how you remember your state, what state you were in. And you save the action. You consult your Q table to see what action you should take. Well, you have to save that so that you remember it for the next time. So as Dave said, the update rule sort of spans two calls to query. An earlier one where you were given a state and you took an action, so you remember state and action, and the current one where you're given S prime, your new state, and R, the reward for that last one. Okay, thanks. Yeah, that's an important one. Yes?
When we are hallucinating the dynamic experiences, we are not taking into account the uncertainty that the real world might present. Doesn't that impact how it's going to perform in the real world?
A very insightful question. So let me repeat it. When we hallucinate a historical experience, actually, let you repeat it because I'm not sure I can state it. It's a good question, but state it again. When you hallucinate the experience.
When we hallucinate historical experiences, it might not be the same uncertainty in the real world that we might face if we were to have that experience.
Right. Yeah. So when you hallucinate this experience, it might not have the same uncertainty as as the actual robot experiences. Here's the thing about that is, if indeed there is some uncertainty, and that you will end up, what the uncertainty means really is, if I'm in a state S and I take an action A, it's not always exactly one S prime that I end up in. There's multiple possible S primes that I'll end up in. That must mean, after you have enough interactions with the world, that you will have multiple experience tuples where that S prime has different values. So imagine we have a list of 1,000 experience tuples. If indeed, let's say there's a 50% chance you end up in one state and 50% chance you end up in another, when you draw randomly from those samples, 50% of the time you'll end up with one that went one way, 50% of the time you'll end up with one that went the other way. So, and the Q update rule is explicitly designed so that as you have those experiences over time, the Q value will end up averaging out between those subsequent states. So long story short is it learns the right thing. Yes?
So we have to set a threshold on the number of real-world experiences that we have had before we start hallucinating this, so that we have the same probability distribution model.
You can you can choose to do that, but well, in fact, if you wait until, say, you have 200 experiences before you start doing that update, that probably is good because your code will run a little bit more quickly. But just in terms of the performance of Dyna, it runs fine if you start doing it right away. So if you only had one experience and Dyna is equal to 200, you'll update that experience, 500 times or 200. But essentially, the more the more of these updates you do, the more quickly Q converges to supposedly what the right answer is. Any other questions? Okay, I'll wrap it up, and I'll be on Piazza if anybody in TV land has any questions, or in Georgia Tech land. And Thursday, yes, we have class, and it's a more formal coverage of Dyna. And remember, next Monday, the robot navigator is due. All right, that's it. Turn this off.
Yeah, I wouldn't gotta walk in front of it. They don't need to see the picture of my face.
This is weird. There we go.